I know, great middle name, right? Anyway, hi, good afternoon. My name is Mike Ryan, Mike Joseph Ryan, in case anyone was wondering. And I'm going to talk to you guys about Bluetooth Smart, also known as Bluetooth Low Energy. Just a sound check. Everyone hear me okay? Okay, good. Cool. Anyway, I had this up for a little bit. There's the slides and more info if you want any of that. So, So, a brief outline, give you some background. What is Bluetooth Smart? Goes by many names. I'll show you some cool stuff, follow that up with a little more cool stuff, and wrap it up. So moving right along, the reason we're here in the first place, sniffing Bluetooth is hard. And it's a fact. It's not as easy as sniffing 802.11 for a variety of reasons. But Mike Osman made this slide 2 years ago, I think, at ShmooCon. And what's interesting is that I'm not here to talk about general Bluetooth. I'm here to talk about Bluetooth Low Energy. And it's a lot easier to sniff, which is great because, it's actually achievable. I'm not sure that sniffing classic Bluetooth is. So anyway, what is Bluetooth Smart? This is by far the most common question I get asked when I mention that I research it. And the short answer is it's a new modulation and link layer for low power devices. And it's important to note that it is incompatible with classic Bluetooth. You can't have a Bluetooth Smart device talk to classic Bluetooth devices or vice versa. They're just completely different beasts at the low level. But at the high level, they use a lot of the same protocols. They both run L2 cap. They both use the attribute protocol. So there's some similarities there. It's been around since 2010. That's when the spec ratified it. I've only begun to see devices in the last year or two. It's also known as Bluetooth Low Energy or BTLE. That's what I normally call it. So if you see anything that says LE or BTLE, it's all talking about the same stuff. It's Bluetooth Smart. So the next most common question is, where is it? And mainly it's in sports devices. Things like heart monitors, pedal cadence, the Nike Fuel Band pictured there on the bottom right. I don't know exactly what it does, but I do know that it uses Bluetooth Low Energy. And then the top right, that's a Pebble watch. Evidently, they're not using Bluetooth Low Energy. I thought they were. I think the next version might. And at the bottom left, that's a pretty interesting device. It's a wireless door lock that uses Bluetooth Smart to let you unlock your door. Wireless door lock. What could possibly go wrong? So, how do we sniff it? Simple answer, we start at the bottom and we work our way up. This is a protocol diagram of what Bluetooth Smart looks like, pretty similar to what you might draw up for IP riding on top of Ethernet or something like that. And we use Ubertooth to get at the bottom two layers, and then we go Ubertooth. Yeah, if you don't have one, you should get one. You should get two. I'm not making any commission off that. They're just really awesome. And so we use Ubertooth to get the bottom layers, and then we pass those up to the PC to handle the top layers. So here's a block diagram of the Ubertooth. And fundamentally, when you want to think about Bluetooth Low Energy, what it really looks like in practice, it's just modulated RF in the 2.4 gigahertz spectrum. PCs really suck at general RF. They just don't have the peripherals for it. That's why Ubertooth exists. Ubertooth handles the RF side of Bluetooth Classic and Bluetooth Low Energy. So the CC2591, the RF amp on the far left, not really that important. It just increases the sensitivity of the receiver. The CC2400, that's the real workhorse of the system. That's a radio chip that translates RF into bits. That handles the PHY layer for us pretty much completely. We configured the CC2400, we don't have to worry about it anymore. And then on the far right is an ARM microcontroller, an LPC17 series. That handles the link layer. That turns the bits. So the CC2400 turns RF into bits. The ARM microcontroller chops up those bits into packets and hands those off to the PC. So in a little bit more detail, the PHY layer is defined as a GFSK signal at 1 megabit a second with an offset of 250 kilohertz. There are 40 channels. It transmits on 37 of those for data packets. And what's interesting is that it uses a frequency hopping scheme. This is the primary way in which BTLE differs from something like Zigbee. Say Zigbee sits on one frequency and just transmits and receives on that frequency. Bluetooth Low Energy uses a simple hopping scheme, but it's still a hopping scheme. So the way hopping works is when a master and a slave are connected to each other, they both hop along the 37 data channels, and they each transmit one packet per time slot. The way you find out, and then they transmit a packet, the master transmits a packet, the slave transmits a packet, and then they jump to the next channel and do it again. The way you find out what the next channel is you take the current channel, you add this value called the hop increment, and mod that by 37, and then you just jump to that channel. So basically you define a sequence of channels. You just basically reorder the 37 channels into a different sequence and hop between those. This is fundamentally different from any of the other low power wireless modes that I've ever encountered. So how do we capture the packets? We just talked to the CC2400. We set its modulation parameters to match Bluetooth Low Energy. What's important to note is the CC2400 is a generic radio chip. It's a lower level than Bluetooth. You can configure it to be completely incompatible with Bluetooth, or you can configure it to be compatible with Bluetooth. Obviously, we care about compatibility. So we set its modulation parameters to be that of Bluetooth Low Energy. But it doesn't actually give us Bluetooth packets. It just gives us bits. So we tune it to the proper channel. We know which channel because we follow the connections. And I don't really want to get too much into how we get the parameters about the connections, because that's a whole other talk that I already gave at TourCon. So if you want more information about that, talk to me after the talk or see my TourCon talk. But we have these parameters that are defined by the connection, the hop increment and the hop interval. So we know how long we stay on a channel. We know when we hop to the next channel. And we know what channel to hop to. So we hop to that channel, and we tell the CC2400, go to that channel and start listening for packets, and it gives us those bits. And that's the phi layer in a nutshell. That brings us to the next level, which is handling the link layer. This is the link layer header as defined in the spec. I know this is kind of boring. We'll get to the good part in a bit. So anyway, here's the link layer defined in the spec. What's interesting to note is, what you want to pay attention to is the access address and the PDU. The access address is a 32-bit integer that basically defines the connection. Any Bluetooth Low Energy devices that are in a connection will have a unique 32-bit integer that is the access address. The PDU is the protocol data unit. That's the actual data that you care about, the data that you want to sniff. So where does the access address come from? That's defined at the start of the connection. That's in one of those connect packets that we want to sniff in order to start following the connection. So let's assume we know that access address. We don't have bytes, we have bits. We don't know where the bytes start. You could be anywhere in that just stream of bits. But we do know what the access address is because we sniffed a connect packet, let's say. So you start searching through the bits that are coming off the CC2400. And you see a bunch of bits and they're just garbage, and then all of a sudden you see, oh, hey, those bits look like my access address. I'm going to keep paying attention. And hey, those bits are the rest of my access address. That means this data is probably the packet data. And with a pretty high probability, that is the packet data. So that's cool. That's the link layer. There's not much to it. So we started at the RF layer, and we converted the RF into bits. We converted the bits into packets. So now what? We'll capture packets to PCAP. So PCAP is the packet capture format used by Wireshark, as I'm sure most of you know. Ubertooth BTLE is the command line tool that we use that speaks packets. So we just use libpcap to dump those packets into a PCAP file, and we slap a PPI header on it, the same way that AeroDumpNG and Kismet stuff 802.11 frames into PCAP files. And that's pretty much it. I'd like to note that I am waiting on a DLT for BTLE. That's a unique identifier for the protocol. You really shouldn't publicly release software without this number. I emailed the TCP dump workers mailing list about this a couple weeks ago. As far as I know, it hasn't. My request hasn't even been moderated yet. So if anybody here knows somebody on that list, can you get in touch with me? Because I'd really like to release this software. So we've got PCAP files. Let's look at those in Wireshark. I wrote some Wireshark plugins that dissect the data. So I had to write a plugin for the low-level BTLE, and then it turns out that there was already a Wireshark plugin for L2CAP and a Wireshark plugin for the attribute protocol. So that was really awesome. I thought I was only halfway done, and then I loaded up my packets in Wireshark, and all of a sudden I've got a full dissection. That was really sweet. So go open source software. But so in this picture, it might be kind of hard to see here, but this is an actual conversation I captured between my laptop and a little sensor board that I was going to show you, but I don't know where it is right now. And this is requesting its name. And if you look way down in the highlighted line on the bottom there, you can see that it's a request for the device name. And then this window shows the reply. The highlighted bytes in the bottom right window might be hard to see, but it says TI BLE sensor tag. So this is an actual conversation I sniffed off the wire using an Ubertooth, dumped it to a PCAP file, loaded it up in Wireshark, and there it is. Now you can actually see it. And this, by far, was the one thing I did that paid off more than anything else in all the stuff I implemented here, because I don't know how many of you have used Wireshark, probably everyone, but it makes understanding protocols so freaking easy. And Bluetooth Low Energy is no exception. And I'm not going to show it right now, but in a little bit I will do a little tour of some of the stuff that I've captured with Wireshark and just show you how awesome these plugins are. But more interestingly, let's talk about injection. Injection is just transmitting packets. So it's pretty much the same thing as receiving. You just turn around the arrows. The data goes in the opposite direction. And it's mostly a matter of following the spec. You create a link layer header, you stuff in your payload data, you hand that off to the Ubertooth, which does all the hard work, and you calculate the CRC, whiten the data, and then the tricky part is how you talk to the CC2400 radio chip. But once you figure out all that detail and slam your head on the desk for like 3 days figuring that out, it's done. And I'm actually going to give you a little bit of demonstration on that. So I have an Ubertooth here. Thank you, Mike Kershaw. And go Kismet. And I'm going to pop open a terminal over here if I can. Let's see. There we go. There's one. There's another. Okay, can you guys read that in the back? It's kind of small, but okay. Oh, yeah, well, that's not important. So I'm going to, over here, start scanning for Bluetooth Low Energy packets. So if I had an actual Bluetooth Low Energy device up here, they would start showing up, but I don't have one up here. And what I'm going to do over here is run this guy in faux slave mode. So let's pick a MAC address. I'm going to use my favorite MAC address. And there it is. This the screen does get a little bit cut off here, but if you look on the other screen over to my right, you can see that MAC address just showed up. And just to prove that I'm not completely full of hot air, I'll hit some random keys here and do like, I don't know, some random number that looks good. And there it goes. That shows up right there. So what you're looking at is my laptop scanning for Bluetooth Low Energy devices, and the Ubertooth just sitting there advertising that it's a Bluetooth Low Energy device with this specific MAC address. And as you can see, my laptop seems to think that that is a legitimate Bluetooth Low Energy device. So that's pretty cool. Let me switch back over here. So the status of that is that, like I said, it does show up. As far as I know, this is the first injection of any Bluetooth system ever that's been demonstrated. So that's pretty cool. Thank you. So right now, it doesn't actually respond to scan requests. What basically what the Ubertooth is doing is sitting there and saying periodically, hey, I'm a device, hey, I'm a device, hey, I'm a device, and it just advertises its MAC address. What the master normally does in that situation, and I'll show you a little bit later in some PCAPs, is that the master is saying, hey, you're a device, tell me what your name is. And it just periodically requests that. And I haven't got that working yet because it turns out that, so I tried spamming out that packet, like, hey, I'm a device, here's my name. Hey, I'm a device, here's my name. Yeah, it turns out that the Bluetooth stack is a little bit more sensitive to timing than that. So it didn't quite work, but we're getting there. Obviously, I'm able to at least convince my laptop that this fake packet is legitimate Bluetooth, so we're getting somewhere. So let's move on to encryption. It's time for another good idea, bad idea. Good idea. Using AES CCM to encrypt packet data. Bad idea. Using a custom key exchange protocol. So key exchange protocols are a pretty well studied area of research. There are a lot of really good key exchange protocols out there. The Bluetooth SIG didn't use any of those. They invented their own. And it's all based around their idea of how pairing should work. And pairing, very briefly, is a process in which you set up a short-lived encrypted session so you can exchange a long-term key. And the three pairing methods that they define, the only difference between them is how they define a 128-bit AES key that is used in the very first stage of setting up that encrypted connection. There are three, like I said. One is called just works. Don't trust anything called just works. It's pretty broken. The next one is a 6-digit PIN. This you would think is a little bit better, and it is a little bit better. It uses a value between 0 and 999,999, 1 in a million, and it pads that out to 128 bits and uses that as a key. Also not that great. And finally, we have out-of-band pairing. That actually uses a 128-bit value that's exchanged out of band by like connecting a wire between your master and your slave or something like that. So this is my favorite quote from the spec. None of the pairing methods provide protection against a passive eavesdropper. So the reason it's my favorite is because it's actually not true. Out-of-band pairing provides excellent protection against a passive eavesdropper. You would have to guess a 128-bit value. Pretty tricky. So, back at TorCon, yeah, it's like guessing someone's middle name. But back at TorCon, I theorized an attack on brute forcing that. Well, it's no longer theoretical. So, the confirm is a value that's exchanged during pairing. It's calculated as it was written up here. You call AES twice on a bunch of values using this TK, temporary key, as a key. That's the key that I was just talking about on the last slide. And the data here, the data in green, is data that you already have. This is data that we sniffed off the wire in plain text. The data in red is the data we want. But wait a second. That data, we know something about that data. It's an integer, a pretty small one, unless you're using out-of-band pairing. In fact, we know something else about it. With just works, they just use 0. So, yeah, anyway, I wrote some code to actually crack that, and the results surprised me a little bit. So let's move over here. Oh, hey, that's still running. Okay, so let's kill this and this. I don't know why this projector isn't showing up right. I can't see a damn thing over there. Oops. Okay, well, don't look at that screen. Look at that screen. But I don't have this screen on my screen, so. Okay, so the tool I wrote is called Crackle, and it does some really cool stuff. And I have a link to this tool in a little bit, but the first thing let's do is crack that temporary key. So what I have here, let's see, what do I have here? So Crackle on LTK exchange. No, what is it? Sorry. I'm freaking blind, so let me just go ahead and take a look. I'm doing great on time, so. Okay, LTK exchange. So, you know what? I'm just going to go ahead and actually show you this file first. So, whoops. Yeah. Tab completion, why must you fail me so? Okay, so one of the great things about Wireshark is that its filtering is awesome. So I happen to know that the pairing occurs over the Bluetooth Security Manager protocol. So, filter by Bluetooth Security Manager, and there you go, there's the pairing conversation. This is a pairing conversation I sniffed with an Ubertooth between my laptop and a device I have. And these are the values that it exchanges. And so Crackle takes this PCAP file and it parses these values out. And it calculates the confirm the same way I showed you on that slide just a moment ago. And it will also decrypt the file. So let's run this with time. Let's see how long that takes. Oh, whoops, I just cracked your temporary key. It took 0.0 seconds. So if you're using JustWorks, that's how much security you have. So just for yucks, so basically I do for I equals 0 to 1,000,000, try this temporary key. For yucks, I do it in reverse to show you the worst case scenario if they're using a temporary key of 999,999. Let's see how long that takes. Oh, what is it? About a second? So yeah, the total time to crack there, about a second. This is the pairing mode that's going to be defined on pretty much every device you'll ever encounter, because out-of-band pairing is pretty cumbersome. So that's bad. In fact, that's it. You're done. With that temporary key, you can derive every other key used in the encrypted session that follows. And usually the first thing that's done during that encrypted session is the master tells the slave, hey, for all of our future communications, let's use this long-term key. It's an encrypted session, so it just transmits the key, well, not in the clear, but in the clear relative to the encryption. But your encryption is broken. We just got your temporary key. So yeah, I'll get back to that in a sec. But the bottom line is your security is dead. Like rigor mortis, habeas corpus. We can decrypt the current conversation, and we can decrypt any future conversation between this master and the slave. And that's not just hypothetical. I actually wrote a tool to do that too. That's also part of Crackle. I'll go back over here. Let me first show you that same PCAP file. After the pairing exchange happens, so after the pairing exchange happens, you see, is that not greater than 0? There we go. So after the pairing exchange happens, there are a bunch of these packets that are, I think they should show up as invalid. I'm not sure. I can't even see that. Hang on. Yes, so let me bring this back over here. So these packets here are invalid as far as Wireshark's concerned because the body of this message here is encrypted. Obviously, it can't parse that as L2-cap data because it's not L2-cap data, it's encrypted data. But remember I said this will also decrypt the file. So that output file there, decrypt LTK, okay, let me filter that on this screen. BTLE.data. There's no magic going on. I'm just writing filters better. So this message right here, contains a 16-bit value that isn't showing up because it's such a big screen. But these are the messages that were just encrypted in the previous slide. or the previous packet capture, they're decrypted now. And that's the long-term key being exchanged. And as a matter of fact, Crackle outputs that long-term key. Jesus Christ, I can't see anything. It's tiny on that screen, it's huge over here, it's horrible. This highlighted value, that's the long-term key, which is pretty nice to have because let's say you capture another file like this one that I have here called encrypted known LTK. That's a further conversation I intercepted between my laptop and the device in question after the LTK had been exchanged. This one doesn't have a pairing session. This one, the master just says, hey, use that long-term key that we established in the previous session. Well, we know that long-term key. So I'm going to go ahead and use that as input, take that long-term key right there, say, use this long-term key. Where's my mouse? Where is it? I'm lost. Use that long-term key, and output that file to there. And yeah, there are some files that we don't properly decrypt, or there's some packets that we don't decrypt yet. I don't know why, but still working on it. This is kind of rough code. But as you can see, it says we decrypted 7 packets. Well, that's awesome. Now let's open up that file. Open up that file. These packets were encrypted previously. After this encryption setup right here, well, now they're in plain text. You can see that this is just the Bluetooth attribute protocol. So Crackle decrypted those using the long-term key that we sniffed off the wire. Not a theoretical attack. I can decrypt all of your encrypted communications using this open source software. Applause. So, like I just demonstrated poorly, Crackle will decrypt a PCAP file that contains a pairing setup that you sniff off the wire. Crackle also will decrypt a PCAP file that has an encrypted session that uses a pre-established long-term key, assuming that you have that long-term key. In the case that I showed, I'd already sniffed that long-term key. So, once again, encryption here is dead. I can crack the pairing temporary key, decrypt all future communications between a device, and I do this 100% passively. These were not active attacks. This is just stuff I sat around sniffing off the wire. It's busted. I don't know why they released the spec this way, especially considering they knew that it was busted. So there are a couple caveats. First off, every session does use a different session key and a couple nonces. So if you happen to start sniffing in the middle of an encrypted session, you can't decrypt that communication. You miss some essential information at the start of the session. But we have a solution for that. You just jam the connection, and then that'll force it to restart and reestablish a new session key that you can sniff. And there is code in the Bluetooth repository, or Ubertooth repository for jamming connections. And it's very effective. It's not hard to jam connections. So that's solved. It is an active attack. However, raise your hand if you're looking for Bluetooth low energy active attacks right now. Liar. And second, the long-term key, like I said, is exchanged once and then reused. This is good for us when we know the long-term key. It's bad if we didn't happen to witness that conversation. Solution? There is a message defined in the spec for rejecting a long-term key. The slave can say, so the master says, hey, please use this long-term key that we established before. The slave can say, I don't know what that long-term key is, in case it lost its memory or something. This attack is still hypothetical. I tried to actually implement it. I just spam out that LTK reject message anytime that an encrypted session starts up. So what happens is this also turns out to be a pretty effective jammer. It's not that hard to jam these guys. And the worst part is, after the session was reestablished, they were still using the old long-term key. So it didn't really meet its requirements. But I'm working on it. This, it turns out, like I said earlier, this is really sensitive to timing. And yeah. So the postscript on that, if you're designing a device using Bluetooth Low Energy, don't rely on just works or 6-digit PIN. As I demonstrated, any hope of any security that you had from those is completely hopeless. It's worthless. Out of band, however, is not compromised, as far as I can tell. And I had an idea. I haven't really thought too hard about this. You could presumably implement Diffie-Hellman in band over unencrypted Bluetooth, low energy, to exchange a key that you use for out-of-band pairing. And if you do that successfully, you should be secure against these attacks. You don't even have to implement your own encryption. The link layer handles it for you. You just have to implement a key exchange. So, yeah, there's some interesting work to be done there. So, to summarize, we can sniff Bluetooth low energy connections. We can inject Bluetooth low energy connections. It's not very rich yet, but we're getting there. We can capture Bluetooth low energy connections to PCAP files and look at those with Bluetooth low energy. We can crack the Bluetooth low energy pairing, and we can decrypt communications that are passively intercepted. Top to bottom, Bluetooth low energy, no security for practical purposes. You can applaud if you want. So some of the future work that I'm looking at with this, Dragorn and I, the Kismet guy, we're working on a Wireshark capture source so that we can just fire up Wireshark, and under your list of capture sources, you'll see Ubertooth and Bluetooth low energy mode. Right now you have to use a command line tool to capture it, kind of annoying, but this will make it a lot better. Also like to flesh out the slave on the dongle so it does more than just advertise its existence. And I'd like to work on master on dongle, because you can do all sorts of evil stuff with that if you've got a fully programmable Ubertooth that's acting as a Bluetooth master. You can freak devices right the hell out. And finally, well not finally, but probably the most interesting thing that could come out of this is a Bluetooth low energy stack fuzzer. So you can craft arbitrary Bluetooth-like packets that are almost Bluetooth low energy but not quite, or some packets that have invalid characteristics, and throw those at some Bluetooth low energy stacks, like the ones found on, say, iPhones or latest Android devices. That's a really big unexplored attack surface. I bet you'll uncover at least some interesting things there. And my favorite, most creative idea for what to do with an Ubertooth. So everything I talked about was implemented, well, almost everything I talked about was implemented on the Ubertooth itself. This does not depend on a PC except for like taking apart the packets, but we can capture the packets fully autonomously on an Ubertooth. So you solder yourself on a micro or an SD card, you slap on a battery, implement the SD spec and a file system on the Ubertooth, toss it in the bushes next to, I don't know, like a wireless door lock or something, and come back a couple days later, and who knows what you could do with that. So I'd like to note, I'm not a fuzzer guy. If anybody has like really interesting ideas on how to approach that, please talk to me, because I'd love to work with you on that. Here's a link to all the software. So the Wireshark stuff, the slides are going to be available online, so if you want to grab those later, you don't have to take a picture of this slide or anything. But so all this stuff is in the ShmooCon 2013 branch. It's still under a little bit of development. I plan on cutting a release of both Ubertooth and libbtbb in like maybe a week. But the main thing holding me back on the Wireshark stuff is the lack of a DLT. So again, if you know anybody involved in the TCP dump project, please get in touch with me on that. Before I wrap up, I'd like to give a couple more little perusals of some stuff that I've captured in Wireshark. So let's kill this guy here. If you've got a beer waiting for you at the bar, you feel free to leave. I don't have much more content at this point. So let's see. So here's me trying to spam that message. So yeah, I'm spamming this message pretty hard, and it goes ahead and encrypts its connection anyway, and I still spam that message, and it doesn't really do anything until it kills the connection. So Here is a portrait of my failure. Please enjoy. What else have I got here? If you're interested in what it actually looks like I have a temperature sensor that I would love to have demonstrated for you up here, but God knows where it is right now. But here are some attribute protocol requests for the temperature data. And then somewhere down here should be a response. So a read response with the temperature data highlighted there. Oh, 0, cool. This was when the temperature sensor was actually off. It said a temperature was 0. But yeah. So anyway, this talk ran a lot shorter than I expected. So I'd like to give some major thanks to people who helped out. Mike Osman and Dominic Spill. Those guys are awesome. Yeah, applause for them. They deserve it. So Mike Osman designed the Ubertooth, and he presented it at ShmooCon, actually, so go ShmooCon. And Dominic Spill is the current maintainer of that. So those guys also, aside from being really cool dudes, they're also really nice, so awesome on them. I'd like to thank Mike Kershaw, a.k.a. Dragorn, a.k.a. the Kismet guy, for helping out on the PCAP stuff, and we're going to do that Wireshark stuff coming up real soon. The rest of the team on Ubertooth, hash Ubertooth on Freenode, really cool people in there. If you want to get involved in the Ubertooth project, join the IRC channel, because it's a really cool, welcoming group. The Blues team for making an awesome Bluetooth stack for Linux, and the Bluetooth Special Interest Group for publishing the spec. That made this really easy. Like, seriously, most of this time was spent reading the 2,300 page spec, which is a really readable 2,300 page spec. And finally, I'd like to thank ShmooCon for giving me this opportunity, and my employer, ISEC Partners, for, go ISEC, for sending me out here and letting me do this talk instead of actually consulting. So thank you to them, and thank you to everybody who came and sat through and suffered through this talk. So at this point, I'll take any questions. Front row.
I'm slightly confused. Do you have to sniff the initial pairing of the devices, or can you track it if I take some previously paired device from home and bring it in here and fire it out?
So the question was, do I have to witness the initial pairing in order to crack the encryption? So number one, if you're not using encryption, it doesn't matter. We can obviously sniff your entire connection. If you are using encryption and you have already established a long-term key by pairing in a Faraday cage, currently I cannot crack that. I have a theoretical attack on that I attempted, where you spam the message that says, I reject that long-term key, and that should force the master and the slave to reestablish, make you repair, essentially, and establish a new long-term key. So currently you're safe as long as you practice safe pairing and pair in a Faraday cage.
Or, just not near you.
Or far away from an Ubertooth.
So
there's another question behind you a second ago. Go ahead.
So why is this pathetic? I mean, Diffie-Hellman came out in the 70s, before I was born anyway. Like, why did they even freaking try in their 2,300 page spec to do something, welcome to the 1980s?
So you have just asked the third most common question I get, which is, why didn't they use something like Diffie-Hellman that's existed for like a million years? And the answer is, I don't know. I've talked to some people involved in the Bluetooth Special Interest Group. My best guess is that it's just a committee beast, and they decided that the subcommittee on pairing would have full authority on defining the pairing mechanism. But your salient point is, would this have been solved by using Diffie-Hellman? Yes, it would have. I don't know why they didn't. Go on.
The repairing, the forced repairing, do you know whether that would theoretically drop the device back into an unpaired state that would require human interaction with repairing, or whether it would be something that would automatically kick the device over?
So the question is, if we forced repairing, would that put the device into an unpaired state that involves human interaction, or would it be automatic? The answer is, it depends on the device. If your device is using something like JustWorks, it's probable that it would automatically repair the next time you use it, because a device that uses JustWorks doesn't have any human input, so you would use that for something like a heart monitor that just straps to your chest. So yeah, it depends on the device. 6-digit PIN, it would probably require you to enter the PIN again. Question?
Another what the hell question, but why the hell do they have things like heart monitors have capabilities like that? I mean, you know, like
I'm sorry. I don't,
like okay, why use an unencrypted connection for heart rate monitors and connecting biomedical devices?
so the question is, why wouldn't you use encryption on something like a heart rate monitor?
It just seems like something that you.
It just seems obvious.
Yeah.
And the answer is, I guess they're lazy. I don't know. Price might be involved. Nipun.
So, what is practical range? How far do they have to be from the target in order to sniff the packets?
The question is, how far away do you have to be to sniff the packets? The answer is, I don't know. I haven't done any range tests on it at all. So the full disclosure is that I don't capture every packet anyway. I suspect it's a configuration issue, but my packet capture rate has been improving. It's hard to say whether if I tried to do range tests right now, it's hard to say whether it's due to a bug in the firmware or due to just dropping off. I have walked away like dozens of feet away and then had the connection drop, get reestablished, and I've picked that up. So, yeah, don't know. Short answer. Any other questions? Going once. Oh, one more.
How about putting the protocol processing on the Ubertooth so that you don't have to spam packets? You can be intelligent about responding.
So the question is, have you thought about putting the protocol parsing on the Ubertooth so you can be more intelligent about responding? Actually, it is on the Ubertooth, and I'm just unintelligent about responding because I ran out of time. I didn't have time to implement it properly. So it's all work in progress stuff. Nothing is finished here. Anything else? Going once. All right, thank you very much.